If we look at a set of final exam scores from a statistics class that are normally distributed with a mean of 63 and a standard deviation of 5, then we can use the normal distribution to answer questions about various probabilities. For example, maybe we want to see the probability that a randomly selected student scored more than 65 on the exam. The first thing you should do is draw a diagram. Draw a bell curve, label the center and the x values for our data set. We know we have a mean at 63, so the center is at 63, and I recommend going 1, 2, maybe 3 standard deviations above the mean, as well as 3 standard deviations below the mean. This will give you a better idea of how spread out your data values are. We're specifically looking for a score of more than 65. So I'm going to draw a vertical line in my diagram that represents a score of 65. And if I'm looking for scores that are higher than that, then I'm looking for area to the right of that value. I can solve this problem using a table of values, but first I have to convert my variable value, the x equals 65, into a z-score. So if I convert 65 into a z-score, I find that the z-value is 0.4. Then from here I'm going to read my table to find the probability that z is greater than 0.4. And we know that right-sided area using the table requires us to use the complement. So from the table we're actually going to read the left-sided area. Doing so, I see the area left of the z-score 0.4 is equal to 0.6554. So 1 minus that gives me the area that I'm looking for. So that means the probability that a randomly selected student scoring more than 65 on the exam can happen at about a 35% chance. Let's say we want to find the probability that a student scores less than 85. Well, we're starting with the same distribution, so I can recycle my diagram. This time, though, I need to find the scores that are less than 85. Now, that's well beyond 3 standard deviations above the mean, so we know that this is a very unusual score compared to the rest of the scores in the data set. And if we convert that x value into a z-score, we'll find that the z-value is 4.4. And reading our table to find the z-value of 4.4, we'll see that z-values above 3.5 result in an area of 0.99. Now notice that for this problem, since we were looking for left-sided area, I did not have to use the complement. However, because this z-score is so large, we're going to kind of exceed the values on our table. Our table doesn't have a z-score for 4.4, so it stops at 3.5, and it says any z-value 3.5 or larger. It's almost 100% of the area, not quite, but very close. So the probability that a student scores less than 85, that's almost certain, almost 100%. I'm rounding up here. We know technically the area is 0.9999. Let's take a look at finding percentiles. If we're interested in finding the 90th percentile, first we have to remember that a percentile is a value in your data set that divides all of the data into a lower group and an upper group. So the 90th percentile is a test score that separates the students below them and the students above them. And we're specifically looking for the 90th percentile. So what test score is better than 90% of the other students, but not as good as the top 10%. Now, we don't know what the test score is, so drawing this in my diagram, I'm kind of estimating here, but I do know that I'm dividing all of the class, all of the test scores into 2 groups, the bottom 90% and the top 10%. And we can use our normal distribution table backwards to find the z-value that corresponds to an area of 90% starting from the left. So let's take a look at our table, and we're going to read through the areas in the middle of the table. So we don't know the z-score, that's what we're looking for. Combing through these areas, you'll notice there is not a single one that's exactly equal to 0.9. But we can find one that's pretty close, 0.8997. That corresponds to a z-score of 1.28. But then there's another one that's pretty close. That's the 0.9015, and that corresponds to a z-score of 1.29. To pick between these two, we're going to use the one that is the closest to the area that we're considering. So since we're talking about a 90th percentile, we are really looking for an area of 0.9 between these two areas. The 0.8997 is closest to what we're looking for, so that's the z-value that we're going to keep. Going back to our picture, notice that we're trying to find the actual test score that gives us that 90th percentile, and so far we've only found a z-score that correlates to the area we want. So now we're going to use that z-score to find the variable value, the test score. So looking for x, we're going to plug in our mean, our z, and our standard deviation to find that a test score of 69.4 is what separates the bottom 90% of scores from the top 10% of scores. So our 90th percentile is 69.4. Let's try another one. Let's look at the 70th percentile. Again, I don't know what test score does this split, but I know that the bottom area would be 70% and the top area would be 30%. So we're going to go back to our table and look for an area close to or exactly equal to, if we're lucky, 0.7. Now there isn't one, unfortunately, but we can find two that are close. One area is 0.6985. That comes from a z-score of 0.52. The other area is 0.7019, and that corresponds to a z-score of 0.53. Again, we're going to pick the one that's closest to the area that we're interested in, which is 0.7. And the area 6985, that's the closest to 0.7. So we're going to use the z-score from that area to find our test score that gives us the 70th percentile. So we have the z-score that gives us the area we're looking for. Now we're going to use that z-score to find the x value. So we just need to plug in mu, z, and sigma to find x. So x is equal to the 63 plus the z-score 0.52 times the standard deviation 5. And that tells us that the test score 65.6 separates the bottom 70% from the top 30% of test scores. So our 70th percentile is 65.6.